Hello, everybody. Welcome to my talk. My name is Timur Doumler. I want to talk to you about contracts and particularly the ongoing effort to put contracts into the C++ standard. I like the ACCU title slide. I actually do have my own title slide, though, so I'm going to switch to that. And the reason I have my own title slide is that it also has the date and the version number in addition to the name of the talk and my name, which is important in this case because this is the third time I'm giving this talk. It's the first time I'm giving it at a conference. The first two were meetups, local meetups, Munich and London. But every time I give this talk, stuff changes because this is ongoing committee work. It's not in the standard yet. So there's like little things that are changing. So this is version 3 or version 0.3 because it's not in the standard yet. So it's a version 0.3. It's not version 1 yet. And probably next time I'm going to give this talk, it's going to be version 0.4 and things are going to be different again. This is a snapshot in time. Last month, we had a committee meeting, C++ committee meeting in Tokyo, Japan, where we made very good progress with this. We are very close to having something that we agree, can go into C++ 26. We're not quite there yet. I'm going to talk about, what is still missing, what are the little things that we still don't agree on the committee. So this is the post-Tokyo edition of this talk here at ACCU. And this is an overview, what I'm going to be talking about. I'm going to first have a little general section about what contracts are, which is going to have some heavy overlap with the talk we just heard from John Lakos here, who was in the room for the last talk. Okay, most people, but not everybody. So I'm going to go through this maybe a bit faster then. And then a little bit about the history and motivation of getting getting contracts into C++, design principles of the current proposal that we have, and then what's in the proposal, like the language spec, the library spec. We're going to go over all of that. And then I'm going to mention what are the open questions currently that we still don't quite agree on yet on the committee, and then what are future extensions that are not in the paper, but will be there later. Maybe in C++ 26, maybe in C++ 29. So what are contracts? It's a concept that was developed in the 80s. Bertrand Meyer was the key person there. It's an approach for software design, which says that you can specify formal, precise, and verifiable specifications for the interface of software components. Some of which are, why is this so yellow, this slide? Is this going to be on the video like this? Okay, well, I think it's readable, so it's fine. So we have preconditions, postconditions, and variants. And those are collectively referred to as contracts in accordance with the conceptual metaphor with the conditions and obligations of business contracts. Now, what is a contract? A contract is a set of conditions that expresses expectations on a correct program, right? If the contract is not fulfilled, the program is incorrect. Now, one type of contract is a function contract, which is a contract on a function, comes in two parts, preconditions and postconditions. A precondition is the part of the contract that is on the side of the caller, what the caller of that function should satisfy in order for the program to be correct. So those are requirements on the arguments you pass in or some other state visible to the function at the moment you call it. And a postcondition is the part of the contract that the function implementation itself is responsible for satisfying. So what does a function guarantee? Maybe the return value or maybe some other state that is observable after the function has returned. There are a few other types of contracts. There's class invariants and loop invariants. I'm not going to talk about those because we don't yet have a proposal to standardize them and put them into C++. So we're going to focus a lot on function contracts. Here's a little bit of terminology as well that is used throughout a lot of talks and papers that talk about the stuff, just to get us all on the same page over like what words we use and what they mean. So as John already covered in his talk, a function that has no preconditions is a wide contract, and a function with preconditions that has preconditions has a narrow contract. And for such a function with a narrow contract, if you call it in contract, then we satisfy the preconditions. If you call it out of contract, we don't satisfy them. An out of contract call is a bug. We also call that a contract violation, right? So let's do this exercise again. Let's see how good you are with this. What functions have wide contracts? What functions have narrow contracts? In the standard library, we all know vector. Vector is a good one. So vector size. Does it have a wide contract or does it have a narrow contract? Narrow or wide? Wide. Okay, good. Vector empty. Wide. Operate a square bracket. Narrow, right? It is always a bug to call vector operator square bracket with an out of bounds index. Operator at. Wide, right? So it's not a bug to call it with an out of bounds index. It's not undefined behavior. It's anything like that. It's perfectly fine to do that. It's going to throw an exception, right? It's not a contract violation. So that has a wide contract. Vector front, narrow or wide? Narrow, right? It's a bug to call it on an empty vector. Vector back? Narrow. Okay. Vector reserve? Wide. It's never a bug to call vector reserve. Vector begin? Wide. Oh, you're good. You're good. You got some practice with the previous talk, so it's good stuff. Vector end? Wide. Vector pushback? Wide. We know this, right? So if pushback fails, it's still perfectly well-defined behavior. It's not a bug. It's going to guarantee that the vector is still the same. It's going to throw an exception, right? It's all fine. Vector swap. Ha, now I got you. Narrow or wide?
Wide.
You know this.
So, and so,
Yeah, you know this. Everybody else. Narrow or wide?
so,
Depends, right. So the standard actually says that if they have the same allocator, you're good. Otherwise, the allocator shall not be swapped and the behavior is undefined unless they compare equal, basically. So it depends on the type, right? It depends on the allocator type, and it also then might depend on whether they actually have the same allocator. Right, so what happens when you have a contract violation? So the first really important thing in this kind of mental framework is that a contract violation is not an error, right? An error is something like corrupt data or like out of memory or some other thing that does not depend on your code, but something that comes from the outside, right? No, a contract violation is a bug in your code, right? It's a bug in the program. So it's very important to separate error handling from contract violation handling. Those are completely different things. And who's responsible for the contract violation? Well, if it's a precondition violation, the caller of the function, as we said already, and if it's a postcondition, then it's the implementation of the function itself. And for the other contracts that we don't yet propose to add to standard C++, if it's a class invariant, then it's on the implementation of the class to satisfy that. If it's a loop invariant, it's whether you implemented the body of your loop correctly, et cetera, et cetera. So what happens when there is a contract violation? Well, that depends. In different contexts, different things might happen. In the C++ standard library specifically, it's undefined behavior, right? So if you look in the standard, and in the preamble of the library section of the standard, it says that precondition is a condition that the function assumes to hold whenever it's called, right? So it's like a very specific interpretation of this broader concept. And violation of any precondition results in undefined behavior. The other important bit here is that the standard doesn't distinguish between library undefined behavior or language undefined behavior. It's just all undefined behavior, right? So if you call vector operator square bracket with an out of bounds index, according to the standard, that's undefined behavior. Anything can happen. And for postconditions, it doesn't really say that, but if a postcondition is violated, that's a bug in the standard library. So that's also kind of outside of the scope of the standard document, I guess. So how do we specify a contract? More often than not, it's specified somehow in the documentation or in the specification of a function, right? And whenever that's the case, we call that a plain language contract, right? So there's different ways to do this. Very commonly in source code comments, right? Just comment above the function, right? The behavior is undefined unless this condition is satisfied. Another way to do this is to do this in a separate specification document. We do this in a C++ standard. Preconditions and postconditions are defined in that separate document, or possibly both, right? You can generate Doxygen documentation from comments and stuff like that. Sometimes it's implicit, it's not written down anywhere, but it's just an agreed upon convention. Like generally, like part of contract of a function is that you can call it from multiple threads simultaneously, and it's not going to introduce a race condition. You don't typically have to write that. That's like an assumed contract, but it's part of the contract of such a function. So this is one way to define contracts, and I would say it's the most common one. Another way to specify contract is in code, right? And when we have some kind of syntactic construct that lets us specify a contract, a part of a contract in code, for the purposes of this presentation, we call this a contract assertion. So these are two really, really important pieces of terminology. When you just say contract, it's a very ambiguous term, so I just encourage us to not use just the naked word contract because it's very vague, like it can mean different things, but instead to talk about plain language contract and contract assertion, right? If it's a contract that's written down somewhere, it's a plain language contract. If it's a contract that you're like expressing in code, it's a contract assertion. So let's just use those two terms. And so contract assertions, contract specifications in code, if a programming language lets us do that, we call that a contract facility. So a contract facility is a feature that lets us do this, right? And it can be a language feature or it can be a library feature. There's a bunch of programming languages that have that as a language feature, like the Eiffel programming language, I think, pioneered this. We have them in D, we have them in Ada. There's other programming language like I think C#, I think, has it as a library, if I'm not mistaken. And so what this paper proposal for the standard that we're aiming to get in CSS 26 that I'm going to be talking about is proposing is to add a contracts facility, a way to express contract assertions in code to C++ as a language feature. Okay. Now, if we have a way to write such contract assertions, like here, for example, a precondition, and this is the syntax we're currently proposing, and I'm going to talk a lot more about how this all works in a second, but if we have such a feature, such a contracts facility, it's important to remember that that typically does not express the entire contract of that function, and that's impossible in general. So typically, if you have a contract assertion like this, it expresses a particular provision of the plain language contract. So the plain language contract has a bunch of stuff, This is a precondition, this is a precondition, this is what the function guarantees, this is what the function upholds, whatever. And then some of those you can express in this way. The way you express this is to basically specify an algorithm, in a kind of general sense, that allows you to either verify that that provision of the contract, that subset of the contract that we are expressing here has been complied with, or whether that particular provision of the contract has been violated, right? So there's an algorithm that lets you determine that. We call that contract check. And so in this paper, P900R6, that we are proposing to add to C++, the way to express such an algorithm is via a Boolean expression, which evaluates to true or false, right? And so we call that Boolean expression, which is the red bit here inside the parentheses, a contract predicate. So that's another word that's going to reappear a lot in this talk. A predicate. So that's this Boolean expression there, which is going to tell you whether the contract has been violated or not. Actually, that particular provision of the contract, because a plain language contract might be bigger than that. All right, so we can check the provision of the contract like this by evaluating this expression. Sometimes, that is very straightforward to do. For example, with operator square bracket, it's just a comparison, right? So we can very straightforwardly come up with a Boolean expression that checks that part of the contract. Sometimes we can do it in code, but it is very expensive computationally, or the act of checking a precondition actually itself violates another precondition or another part of the contract. So for example, you might have a binary search, which is log n, but then the precondition is that the range is sorted, but verifying that the range is sorted as log n is not log n, but actually on, right? So that, checking that would actually break the other parts of the contract of that function, the guarantees that it provides about algorithmic complexity. And so you probably don't want to just check that precondition everywhere, even probably in your debug build. Maybe you want to check it only in a special super debug build or something like this, right? Depends on what you're doing. Or maybe you don't want to check it at all, but you still want to have it there in case one day you do. Sometimes it's not only expensive, but actually impossible to check just with a C++ expression without some kind of additional instrumentation like a sanitizer. Like, for example, a very, very common precondition is that this pointer points to a valid object, right? But we can't write a C++ expression that verifies that. That's just not possible, right? So you have to do something like a sanitizer where you have a bunch of additional instrumentation that tracks the memory, which obviously has a huge impact on performance and size and everything, in order to be able to check such a precondition programmatically, and sometimes you just can't do it, right? Imagine a function that takes another function, and the precondition is that that other function halts, which is the halting problem, right? There's no algorithm to do this in general. So you can't check it programmatically. So again, contract assertions in general, they only specify a subset of the plain language contract, right? So that's, again, this distinction between plain language contract and contract assertions. And contract assertions typically only express and specify a subset of the plain language contract. That's very, very important to remember. Right, so now we are moving forward to okay, let's take these concepts and see how we can build a feature for C++ that actually lets us do this. So I'm going to talk about the history of that and why you would want to do that. Turns out C++ actually does already have a contract facility. Who knows what that is? It's assert. Yes, C assert is a contract facility. It lets us express preconditions, postconditions, assertions in code and check them. Right, that's a contract facility. So, I mean, it's a very limited contract facility. So you can't put, for example, a precondition check on a function declaration on the interface. You have to put it in the body, typically as the first thing. Very often you see assertions as the first thing in the function body. You can't customize the behavior when the contract violation has been detected, right? It's just it can do two things, right? If any bug is is defined, then it's just going to token ignore the entire macro, and otherwise it's going to call abort. Like print something to std out and call abort. That's what's std error, I'm not sure. And call abort. That's all it does. You can't customize that. There's no information about what happened programmatically available, right? You can't query in code like what went wrong and where, like that's just not there. And also it's a macro. Macros have lots of problems. There's certain things like curly braces with a comma that you just can't put there because it's going to break the parser. If you like ignore them, they're actually going to be token ignored, which means you might get bit rot because that code is actually not being compiled; it's being just removed textually. An even nastier problem with macro assertions are ODR violations, right? If you have the same function, you compile it once with assertions on and once with assertions off, and then you link those together in the same program, you're not going to have a good time. And like for all of those reasons and more reasons, we really need a contract facility as a language feature, not as a library feature in form of a macro. So we can put precondition, postcondition assertions on declarations, on function declarations. So we can use these things portably across different code bases, across different libraries. Right? So there's like one way to do this that everybody can agree on, that works across API boundaries. We can customize the behavior without running into ODR violations. So yeah, and we don't want to like macro ignore stuff. We want that code still to be checked by the compiler to avoid bit rot, right? There's this problem that if you have some assertions that are just off for a while and then you like, undefine and debug, then everything just explodes. Like you don't want that. You don't want that code. You want that code to be parsed, even if you don't actually check the predicate. And you want some information about the contract violation to be available programmatically, so you can do something with it. You can have some custom function that phones home and tells the server what line of code the violation was and stuff like this. And the other reason why you want this as a language feature is you want that to be accessible to tooling, right? So you want like the entire ecosystem to agree the syntax, how you express these things, so that an IDE, for example, can like nicely color them and have like a little pop-up. Here are the preconditions and postconditions of that function. Or a static analysis tool can go ahead and do something with them, right? Because it knows what they look like. So these are all very good reasons why you want that as a library, the language feature rather than as a library feature. So CSRT has been around for like 40 years. We want something better. So for already 20 years now, people have tried to put this into C++. It's a very long and storied history behind putting contracts into C++. So the first proposal to add a fully featured contract facility as a language feature to C++ was actually by 2004 by Thorsten Ottesen. That's 20 years ago, okay? was this paper in 1962. And he basically was inspired by D, the D language, and the proposal was basically let's take the way it's done in D and just do that in C++. So it looks something like this, where you have these precondition and postcondition blocks, like one each, and then you can put different statements into those blocks. It went on for a couple years, but like it was way before my time on the committee, so I'm not exactly sure what happened to that proposal. Kind of the paper trail just goes cold at some point. I think it kind of fizzled out, but because there were not enough people to help out with actually specifying this, and so that it's like or can be put into the standard. So it kind of fizzled out. Then there was a second phase. It's a bit like with the the MCU, the Marvel Cinematic Universe. It has like different phases, and like it's like this. Like this is phase 1. Phase 2 was an effort by John Lakos and a bunch of other people from Bloomberg to standardize something that is very similar to what they have in their BDE library, which are these kind of macros or macro-like entities that were proposed for the standard library. So they don't go in interfaces, they don't go in declarations, they go in the function body. But they can do more than just good like old C assertion macros. They're like more configurable. There's more stuff going on there. This was like the syntax also went through a bunch of iterations. I think initially it was in all caps. Now it was changed. The last iteration of this had this syntax, which ironically is a syntax that we now have also in the latest proposal. That went on for a couple of years, that effort, but then horribly failed in plenary because people didn't want anything resembling macros in the standard library. From the ashes of that project and some other work that simultaneously has been going on by Daniel Garcia and Gabriel Dos Reis and a bunch of other people like were in parallel working on another way of doing this. So they all kind of joined forces, and that launched phase 3 of the epic Let's Standardize Contracts for C++ saga, which went on until 2019. And they got as far as actually getting into the C++ 20 working draft. It had this attribute-like syntax with these double square brackets, expects for preconditions, ensures for postconditions, and assert for kind of mid-function body assertions. And that went all the way into the working draft. Then some issues were discovered with it, and then people didn't quite agree on what these issues are and what the right way is to fix them. And yeah, we had this meeting, I think it was summer 2019 in Cologne. We had a committee meeting where things got quite a bit heated. And at the end of that, basically the entire feature got ripped out of the working draft. And that was the last meeting, like the feature freeze meeting for C++ 20. So the result of that was that none of it made it into the standard. And a lot of people were upset and sad. That was also kind of the time around which I got dragged into all of this, because like, oh, okay, well, how hard could it be? Let me try and figure this out. Yeah. So here we are today. That was that was kind of the epic conclusion of the third phase of the first three phases of this saga, and then that kind of launched phase 4, which is where we are today. Which is we call this the contracts MVP. This is the latest effort that's been going on also already for 5 years now. So what happened in Cologne after 2019, after the feature got ripped out, is that we actually created a new study group on the committee. So we have this kind of 3-tier structure on the committee. We have actually 4 tiers. At the very top, we have the plenary, which is everybody votes and we agree on this goes into the standard. Below that, we have the wording groups, which approve the wording. Below that, we have the evolution groups that approve the design for library and language separately. And below that, we have these study groups that are doing kind of work that's more kind of specific to one topic. And we started SG21, which is the study group for contracts, which I am chairing together with John Spicer. And so that started in 2019. And the first thing that we did there was we realized that one of the reasons why it took so long and we still didn't have anything that people agreed on would be good enough for the standard is that people didn't really agree on what contracts are for, like what you're supposed to do with them, how you're supposed to use them. So there was a lot of disagreement on that kind of very basic question, like, what are they for? So we went and looked into this. There was this paper from early 2020 where we collected use cases for a contracts facility. And that paper lists 196 use cases. And we did then an electronic poll where we asked the committee which of these use cases you consider more important or less important or like a must-have or don't care about this. And quite a few people actually clicked through all of 196 of them. And so we kind of ranked them. There was a huge effort going on. So yeah, 196 use cases, but most of them kind of fall into 5 buckets. First one would be, okay, we want to have a contract facility so we can document contracts in code rather than in plain language, right? So people can read it, but also tools can read it. That's good, right? Second motivation is that you want to check those things at runtime, much in the same way you do it with assert today. You can turn checks on, and then, if any of those checks fail, you get something you can do something with. People also want to use them for static analysis, so that a static analysis tool can go ahead and say, okay, this function is calling this function, and this function has this postcondition, and this function has that precondition. And I can kind of tell at compile time or like during static analysis time that like you might not actually satisfy this precondition here. Like there is like a logical thing where, this might not be satisfied here. You might have a bug here. And then the kind of more extreme version of that is formal verification, right? Where you can actually, for certain limited problems, formally prove that the preconditions and postconditions and assertions will always be satisfied. And then the 5th use case, which is kind of independent from all the others, is that people want to, instead of checking contracts, they want to assume them, basically have a way to tell the compiler, okay, I know this is always going to be true. So just don't check that and just basically optimize based on the assumption that this is always going to be true, and then we get faster code, right? And so, I mean, this is essentially what happens today with like vector operating square bracket, right? Like the compiler can assume that you're never going to call it out of bounds because that's undefined behavior. Undefined behavior can never happen. So, the compiler is free to optimize your program based on the assumption that that's never going to happen. And then you get weird things that can happen. So those are roughly the 5 buckets of things that people want to do with contracts. And of course, as it always is, it's not actually exclusive to contracts. I think it's with kind of other big features as well. But I think with contracts especially, what happens in the committee is that people want everything, right? So they want this thing, I don't know if you're familiar with German folklore, but there is this mythical beast in German folklore, which is called the egg-laying wool milk pig. The German word for this is more fun. It's obviously one word. So it's like this thing that just does everything simultaneously and satisfies all the needs of everybody, right? And then when you're in this situation, you realize, well, we can't do that because if you want to do all of this, it will take us another 20 years to agree on like whether this is the right specification for that. And, the rate at which new like issues come up will be faster than the rate at which we can agree on solutions. And so we will never be done. And this will never be in the standard, which is kind of what has been going on. But then we realized, okay, well, maybe we don't have to satisfy all features in the first version. Maybe we can do something more limited first and then add to it later. And then once we realize that, stuff gets better. And then the next problem that typically happens, I think this is kind of like socio-psychology. It doesn't actually have much to do with C++, but it's one instance where you can see this playing out, is that typically once you realize that that the egg-laying wool milk pig is unattainable, and you have to limit yourself to something, the next thing that happens is this. This is something that comes from Russian folklore. So anybody who grew up in Russia will know this. This is the fable of the swan, the pike, and the crab, who are like this cart with something really valuable in there, so they want to get that home so they can get to the valuable stuff inside, so they kind of pull it from wherever it is, but everybody's pulling in a different direction, right? So the swan is pulling upwards towards the sky, and the pike is pulling down to the river, and the crab is going sideways, and then basically this kite is not going anywhere. So we had to overcome that problem, but we kind of did that. So we kind of agreed that, okay, we can't get everything, so let's limit ourselves to those things. And we managed to actually agree, okay, those are the things we want in the first version, and the rest we can tackle later. And that gave rise to the contracts MVP, which is what we call the current proposal. It's a minimal viable product, so it does not yet support all the use cases, but we explicitly design it for extensibility. So whenever somebody says, oh, but I want this other thing which is not here, instead of saying, okay, we're going to add this now and going to spend another 20 years arguing about how to specify this and nobody's going to get anything, we say, okay, here's an evolution path how we can do that afterwards. Let's first standardize this, and then, but it's designed in such a way that you can add this other thing on top in cplusplus 29 or whenever. And it already provides immediate value for enough people that it's worth specifying and standardizing, but not for everybody. It doesn't satisfy everybody's use cases, and that's okay, because we can do that in the next version. So the latest public version of this proposal can always be found at this URL. Like in general, that holds for every paper number on the committee. It's like usually P something something number. Whenever you see that, you can type wg21.link/paper number, and then you get the latest version of that paper. And if you put R number, then you get a specific revision as well. So we are currently at R6. That's the latest published version as of now, April 2024. So that's the version where ACCU actually agreed that this is what you want to put in the standard. And then we forwarded it to the next level on the committee. Remember, there's this 4 tiers. So the next level is Evolution Working Group and Library Evolution Working Group. That are the non-topic specific groups that look at all the features and approve the design of those features. So they looked at our design and they had a few, let's say, questions that need to be addressed. So now it's going back to us. So it's going to be an R7 very soon, I guess in the May mailing next month, that addresses that feedback. We already addressed some of it, but we didn't publish that yet because it's still kind of in the middle of that process. We have telecons every week. So yeah, we have to address the feedback from those groups. So going back to these 5 buckets, so what does the context MVP give us? Obviously, it's going to give us self-documenting code because there's a syntax to put these contract assertions on things, right? So you get that. Humans can read it, tools can read it, IDEs can read it, et cetera, et cetera. We also get the second bucket, which is runtime contract checks. So we're aiming for this to be a better replacement for CAssert. So you should not have to use CAssert anymore. You should not have to use custom assertion macros anymore. Who here uses either CAssert or custom assertion macros in their code base? Yeah, that's almost everybody. I have personally never worked on a code base that didn't use some form of assertion macro. Mostly custom because CAssert is just kind of too limited. So hopefully none of us will ever have to do this with macros again. Gives you customizable behavior, can go on declarations, all of the stuff, no macros. Now the remaining 3 buckets, so we don't explicitly not support them, but we don't have any facilities in the first version specific for those cases. Like, we have a syntax which a static analysis tool can consume and do something useful with, and that's great, and we hope that they're going to do that. But we don't have any features specifically targeted at static analysis. For example, we don't have any feature where you can say, oh, this assertion, it needs to be evaluable at compile time so the static analysis tool can definitely do something with this, right? We don't have that feature. We might add that later or maybe not, but currently we don't have that in this paper. And we also don't have a way to tell the compiler, okay, you know what? I know this is always going to be true optimized based on that assumption. Like, the compiler can offer that mode. There's an extension, and we might add it later. In fact, I very much hope we will, but not in this kind of first version of the context MVP that we are aiming to get into cplusplus 26. So what happened before Tokyo, which was the committee meeting last month, is that ACCU agreed this is the design we want. We approved it, great. We forwarded it to the next level. And yeah, as I said, they had some feedback, so we have some more work to do. If you look at the timeline, this is kind of the cplusplus 26 kind of release schedule. Like we have 3 committee meetings per year. We are currently here, right? So next one is going to be in June, the second meeting of 2024 in St. Louis. And we have 3 committee meetings left before the evolution study group needs to approve this design and forward it to the verdict groups. And if you miss that deadline, it's not going to be in CSS 26. So we have 3 more committee meetings to figure out our differences with the evolution groups. I'm pretty sure we're going to get there. 3 committee meetings is a lot of time. It's basically a year where we can do a lot of work. We also work obviously a lot in between these meetings. So I'm fairly confident that we're going to get this into CSS 26. Obviously can't be 100% certain, but I very much hope we do. I think it's very realistic. We are doing a lot of work. We're meeting every week. So we're good. Right. Design principles. So how did we design the context MVP, and what are the guiding principles, the guiding things that we want the design to fulfill, right? So before we talk about the concrete syntax and stuff, we're going to talk about that in a few minutes. Let's talk about, how we designed this. There's a few things that, for example, the previous CPlusplus 20 proposal did in a certain way, where we said, maybe that's not a good way to do this. And not just like concrete properties of a specification, but more like on a meta level. Yeah, this approach maybe is not good. Maybe that's part of the reason why, it then blew up horribly in Cologne. Maybe let's not do that again. So one of those principles is that contact assertions are there to help identify bugs in existing programs, right? So you have a program which might have a bug, you add contact assertions to it, and you turn those checks on, and they should tell you if that program has a bug. What they should not do is to change that program and make it into a different program, right? Because then you're not checking the program you wrote, you're checking some other program, right? So adding a contact assertion to your code should not change the compile time semantics of your program, because otherwise it's going to be a different program. Obviously, at runtime, like if you're checking something, you're evaluating code that you're not otherwise evaluating, that's fine, but it shouldn't fundamentally change what your program does. And to be very concrete, there's like 3 sub-principles here. One is something that Josh, one of the other authors of this paper, calls concepts do not see contracts. So contract annotations should not be seen by concepts, right? It shouldn't change whether a concept, which is a compile time thing, is satisfied. Contract annotations should not affect overload resolution. You should never have a situation where you add contact assertion to an existing program, and that will trigger another overload to be chosen, right? Those things are really bad, because then maybe the other overload that's going to be chosen does not have a bug. So you're looking for a bug, you add a contact assertion to find a bug, but then you end up with a different overload that doesn't have the bug. And then you turn it off again, and then you have the bug again, so that you get like a Heisenberg bug, right? We don't want that, that's bad. Like if we ended up in that situation, then we failed to provide a feature that finds bugs in programs, right? So we don't want adding a contact assertion to affect overload resolution, affect type traits, affect the result of a no except operator. That's an important one, whether no except is true or false. There's an operator that you can branch on at compile time. We don't want to end up in a different branch just because we added the contact assertion. That would be very bad. We shouldn't be able to sphere on it, etc., etc., etc. So the other sub-principle is a zero overhead principle, which means that if you add a contract assertion, actually this says annotation, this is outdated terminology. We don't call them like that anymore. We call them contract assertions now. I'm going to fix that on that slide, apologies. An ignored contract assertion should not cause additional copies or destructions of objects or other code to be performed, right? Obviously, if you're checking the predicate, you will perform extra operations because you're evaluating a Boolean expression. But if that check is off, if it's not doing anything, if you decided to not check it, then the mere presence of the contract assertion in your code should not lead to more work somehow being done than it would be without that assertion being there. And we're going to see a case later where that might happen, and we have to add a special rule to make that not allowed. And then the third sub-principle is semantic independence. We don't want to have a facility in the standard that lets you basically detect at compile time whether checks are on or off, something like any bug that you can branch on at compile time. We don't want to have that kind of feature because then you could circumvent this whole principle and do bad things, and we don't want that. Of course, when reflection enters the arena, it's going to be interesting because you might want to reflect on whether, for example, a function has preconditions. That would be very interesting. And we don't necessarily want to preclude that because if you are reflecting on something, then you are kind of already saying, okay, I'm just going to look at the language from above and do some stuff that I'm not otherwise able to do. So I think reflecting on contract assertions is fine, but we need to be very careful, like what we allow there and how it's going to work. And it's fine because the reflection people told us that they're not going to plan to add, the ability to reflect on contract assertions for CPLUS 26. Like reflection is heading for CPLUS 26. It's very exciting, but like there's not going to be initially a feature there to reflect on contract assertions. So we have a little bit more time to figure this out, which is fine. So in CPLUS 26, there's not going to be an ability to reflect on the presence of contract assertions or whether they're enabled or disabled or something like that, which is good. Another principle, compatibility with existing code. We don't want to break stuff. I mean, that should be obvious, but maybe it's not obvious, so we need to state this. This is something that, for example, the CPLUS 20 iteration of contracts did very badly. A lot of stuff there was defined to be undefined behavior. If a predicate has side effects, that's undefined behavior. If this happens, this is undefined behavior. This is one of the reasons why that didn't go well. So one design principle that we have is that we are not intentionally introducing new undefined behavior to the language with this feature. Okay, we're not doing that. So adding contracts to the language should not add UB that wasn't already there before. And the other thing is that we don't want to break ABI, right? So if you have a function and you have a declaration of that function, and then you have a binary that has an implementation of that function, and now we add precondition, postcondition checks to that function declaration in the header, we don't want the ABI to break. You should still be able to compile with like that binary. Right? We don't want the ABI to change. So adding those things should not be an ABI break. And here's another set of principles. How the contract annotations, again, this should say assertions. I really need to fix those slides. Relationship between contract assertions and plain language contracts. So this is kind of stuff that we partially already discussed. So precondition, postcondition specifiers are specifying a subset of the plain language contract of a function. But what's really important here is that they specify a subset of the plain language contract of that function and not some other function. So we don't want contract assertions to somehow appear from somewhere else and then all of a sudden assertions being there on things that are actually not part of the plain language contract of that function, which is, it's going to get interesting when you start interacting with inheritance and things like that. Another one here is if you have a template, function template, and it has preconditions and postconditions, and you specialize that function template, you have a specialization. You don't want to just automatically get the pre and post conditions from like the primary template because you're specifying a different function. You don't want them to just be pulled in without your knowledge. No, you want to specify your own function contracts. So function contract assertions are specifying a subset of the contract of that function that you wrote, where you wrote them. Okay. The other thing is it's kind of a long-standing confusion, I guess, whether if you have pre and post conditions on a function, whether that's part of the interface or that's part of the implementation. And whenever people are arguing about this, it's a symptom of kind of, you're thinking about this wrong. They're neither. They're both at the same time. They're like the thing that's in between, the thing that like connects the interface and implementation, decides what things can go through that boundary, right? So that's why, for example, pre and post conditions can be specified on the declaration, which is part of the interface, but they can also refer to private members, which are part, for example, of a member function, which are part of the implementation, and things like that. So they're the thing that connects interface and implementation. They're not part of either, and they're part of both. That's the right way to think about this. And finally, we already discussed this. Context assertions are not, they're there to find bugs in your program. They're not there to control program flow. That one is really, really important. If you want to control program flow, there's a great feature in the language for that, which is called an if statement, right? So context assertions are not there to do error handling, to do input validation, to do things that you always want to do, right? Because you can turn them off, right? And then it's as if they were not there. And you don't want your error handling to disappear if somebody has a different compile flag, right? So if there's something that always needs to happen whenever you run your program, use an if statement. Don't use context assertions. Context assertions are the salient kind of difference between context assertions and if statements or things like that is that you can turn them off. And the decision whether or not to turn them off is not made in the code, but it's made when you compile the program, right? So that is the one kind of key difference between context assertions and all the other language features that we have. So if that's not what you want, then don't use them. And this is the last slide about design principles. We designed the context MVP for extensibility. So whenever somebody says, I want this, and we're like, well, we don't know yet how to do this, or like, this is a huge amount of work. If we do this now, we're not going to get this feature in the CSS 26. Whenever we hit something like this, we're going to be like, okay, but we're going to make sure that we can add that later, that we don't close that design door. We're going to like keep the design open so that we can extend it later. That's super important. This whole like thing has been designed with this requirement in mind. And finally, whenever we're not sure what to do, it's like, oh, we could do this or we could do that. And there's really good reasons to do this and really good reasons to do that. And they're mutually exclusive. And we're not sure what the right trade-off is, or we don't agree. We just make the whole thing ill-formed, like, so that we don't paint ourselves into a corner, and then we can decide later. So we don't choose one or the other if you're not sure. And we also don't make it unspecified or undefined behavior, because that's just bad for the user. We just make it ill-formed instead. Right, so now let's dive into the actual specification. Am I about half my time is up now, right? Is that correct? I started at 4? Okay. So now we're actually going to talk about what's in the proposal, which is what you've all been waiting for. So thanks for bearing with me for the last 45 minutes. That's what is actually being proposed. So we have this syntax, pre, parens, Boolean expression, to specify a precondition assertion on a function. We have post parens to specify a postcondition assertion. And that one has a little extra feature. You can put like any name that you want, for example, R, to refer to the return value, to the value that this function is going to return. And you can use that. You can give it a name, like R or red or whatever, and then you write colon, and then you write your expression, and then you can use that there. That's optional, right? You don't have to write the R colon. You can just omit that. Like, not every post condition needs that, right? So for example, the post condition of empty on a vector is that size is equals 0 afterwards. It's not talking about the return value. That's fine. So that's optional. Pre and post are contextual keywords. They're not full keywords, which is really important. It means that it's not going to break your code to add this feature. Like, whenever you use pre and post as a variable name or a function name or whatever, it's all still going to work. They're all only going to be passed as contract assertions in that exact syntactic position, which is the last thing before the semicolon, or if it's a definition, the last thing before the opening brace. Only in that position are they passed as contract assertions. Otherwise, they're passed the way they're passed today. Nothing's going to break. We made sure that this works. So yeah, they can go on declarations. They can go on definitions. They can also go on lambda expressions, because those are kind of also functions. If you put pre and post on a lambda expression, it applies to the operator paren of that, the underlying closure type. And then we have a third kind of contract assertion, which is called contract assert. And it's different because it's not going on the declaration. It's going inside the definition. It's a statement. That one is quite similar to macro assert, except it's not a macro. And so contract assert is actually a full keyword, and we need to do that so we can disambiguate this from a function call expression. And it's also not assert. Like, we really, really, really wanted to use the assert keyword for this, because that's what every other programming language does. Unfortunately, that is already taken by the assert macro. And we spent quite a lot of time trying to figure out because the fun thing is contract assert by default is doing exactly the same thing as assert. Like it checks the expression, and if that's false, it prints something to spit out and terminates, right? So it's exactly the same behavior by default, right? You can obviously customize it a lot more, but so we were like, oh, can we somehow shoehorn like macro assert into this so we can reuse the macro, like the assert keyword and have this, and it's kind of, it turns out it doesn't really work because as soon as you define ndebug, like it's doing something else, and yeah, basically we can't break macro assert, and we can't also have code that means different things in different places. So we had to choose a different keyword. We spent a lot of time trying to figure out what would be a good keyword that's not assert. We looked at 100 different keywords. We ranked them all according to 10 different criteria. It was a lot of work. And at the end, we agreed that contract assert is the best match here. So that's the keyword we now have. The other difference between assert and contract assert is that contract assert cannot be used as an expression. It can only be used as a statement, right? So you can't put it as a sub-expression inside like an initializer or something like this. There's a workaround. You can like put immediately invoke lambda and put that in there. It's a bit ugly, but you almost never want to do that. That's fine. I don't think that limitation is really important. If you want to know why it's not an expression, I'll tell you later at the bar. It's a long story. It's quite entertaining. Why it can't be an expression, but there are reasons. So we have these three kinds of contract assertions. We call them contract assertion kinds: pre, post, and contract assert. So pre introduces a precondition assertion, post is introducing a postcondition assertion, and contract assert is introducing an assertion statement because it's a statement. So those are the three assertion kinds we have. Precondition assertions and postcondition assertions are collectively called function contract assertions because they go on functions. And then all three together are collectively called contract assertions. The terminology is maybe a tiny bit confusing because we have keyword contract assert, which is an assertion statement, but then contract assertions are all three of them. We know that this terminology is not absolutely perfect, but we argued a lot about this and nobody has any better ideas, so this is what we have. So let's talk about function contract assertions, pre and post. So there's another conceptual thing here, which is really important to distinguish. People confuse this. I was confused about this for a while. Really important. So a precondition is usually expressed by a precondition assertion, but not always. It's again this difference between contracts and contract assertions, right? Preconditions and precondition assertions. A precondition is the conceptual thing. A precondition is a conceptual plain language contract that your function has. A precondition assertion is the code thing, and they don't map always one-to-one to one another, right? So precondition and postcondition conceptually, the difference between them is who's responsible if it fails, right? Is it the caller or is it the callee? Precondition and postcondition assertions are distinguished by when are they evaluated, when a function is being called or when a function returns, right? So it's a different difference there. So for example, you might want to use a assertion statement to check a precondition. And there are even rare cases where you want to use a postcondition assertion to like check a precondition because it's just cheaper to check that precondition after you've run the body of the function algorithmically in some cases. So then you're going to use a postcondition assertion to check a precondition, a conceptual precondition. Nothing wrong with that. Just remember, preconditions and postconditions are the conceptual thing. Precondition, postcondition assertions are the code thing. Now, where can you put these things? So you can put them on function templates. You have to put them on the first declaration of the function. If you have redeclarations, for example, a definition further below, you can put it there, but it's optional, right? If you have deduced return type, you have to put it on the first declaration, and that has to be a definition because otherwise you don't know what the return type is, and then you can't refer to it in a postcondition. You have to know what the return type is. You can put them in lambdas, and contract assert you can put anywhere you can put a statement. There's a few limitations. You can't put pre and post on deleted functions. Doesn't make sense. You would never evaluate them. You can't put them on functions that are defaulted on the first declaration because equals default, basically you're saying, I want to have the default implementation, and that doesn't, and the default interface as well, and that doesn't contain any contract assertions. And if you were to allow this, there would be all kinds of problems with like what happens when you add pre and post to like a trivial constructor, for example, is that then no longer trivial? Or like a trivial copy constructor that you can replace with memcopy, but then you wouldn't check pre and post anymore. So yeah, it's kind of a bit of a can of worms. So we just said, let's make it all formed. You can't do it. We can't put them on virtual functions. Now that's a limitation that we're hoping to resolve soon. We just haven't figured out yet how to do this. You can't put them on function pointers. That we just don't know how that would work. Like that's not clear at all. But if you call a function through a function pointer, even though the function pointer doesn't know about the pre and post condition assertions, they will still be checked. So don't worry, they will still be checked, even if you call through function pointer or through the function or some other indirection mechanism. And you can't have pre and post on coroutines, again, for complicated reasons that I don't have time to explain. It doesn't quite work. Contract assert is allowed inside a coroutine in the body, but you can't have a yield or weight expression inside the contract assertion predicate. Again, for reasons. But if it's in a nested lambda, it's okay because there's not the suspension context of that function. Those are all technical details I don't think I have to go into right now. Those are kind of like little corner cases that we have to fix. There's a lot of that in the paper. Okay, that's the syntax. Semantics, like what does it do? How does it work? Name, lookup, and access control is the first thing. Like it happens for pre and post as if it was the first statement in the body, which means that you can access private members. Another one, which was slightly controversial, but we in the end agreed that this is the better trade-off, is we decided that local variables are implicitly const in a precondition, postcondition, and contract assertion predicate. So it's a little bit like a const member function or maybe a lambda where you capture something that's by default const as well, right? So if you're trying to assign to local variable inside a contract assertion, that's not going to compile until you can obviously you can put a const cast around it and like circumvent that, but don't do that. That's just like you don't want to modify things in contract assertions. That's not what they're for. They're for checking things, not for modifying things. So referring to the result value in post, so if this R thing, like what is it actually? Is it a copy? Is it a reference? What is it? It's neither of those things. And the best way to think about this is it's like the name in a structured binding. It's another name for an entity that has been declared elsewhere but didn't get a name there. So it is very similar to a structured binding kind of identifier in that sense. It's a name for an object that has been declared elsewhere. In this case, it's a name for the return object of that function. Again, it's implicitly const. You can't increment the return value of a function inside the post-condition assertions. That would be a very bad thing to do. That's not going to compile unless you put const cast around it. Please don't do that. So yeah, this is the standardise way of saying this is an L value of type const t referring to result object. What else do we have here? Oh yeah, it has some interesting properties. So basically, if you have at the bottom there, if you initialize a variable with some kind of initializer and that calls a function, it turns out that this object on the left-hand side is initialized before the arguments of the function are destroyed, and the arguments of the function are destroyed before and the post conditions are evaluated before that happens. So basically, after. Okay, I'm confused now. So basically, y here at the bottom is initialized before you check the post condition of f. So that's a bit weird, but it works. I'm not going to dive into this now. I have a lot more slides, but it's all in the paper. But you can do these really interesting things with it. Like, don't do that. Just like to demonstrate how it works, like what the mechanics are. If you have x and then you initialize x with f and you pass the address of x into f, then by the time you get to the post condition of f, x has already been initialized, right? So then that post condition will actually always succeed, which is surprising. But that's how it works. Except if x is trivially copyable, because then, like, in order to not have an ABI break, that's again one of our principles, we need to allow x to be passed in a register, in which case that might not work. That's already an exception we have in the language, so we just apply it to that here. If this is confusing, like, look at it in the paper. It's all explained there. It's kind of weird corner cases of the language, and for each one of those, and there's a lot of them, you have to like make sure it works in a way that fits into the rest of the language. This is about, not being able to refer to the result value if you have an auto return type, you don't know what that type is. I already covered that. Oh, this is an interesting one. So if you refer to parameters in a post condition, those parameters have to be declared const, otherwise it's not going to compile. And that's a really, really important rule. Like, this is a clamped function, right? You get min, max, and v, and then you return a value which is v, but not smaller than min and not larger than max, right? So you clamp it to this interval. Hopefully people are familiar with this. These are the post conditions of that function, right? Hopefully that's also not surprising. But if that were not const, if you could write this, you could then satisfy those post conditions by just doing that, right? Post conditions would pass. You don't want that, right? So also that body could be in a different, could be somewhere else, right? So you could, if you look at the declaration of this function and you look at parameters and you have these, you refer to these parameters in a post condition, you want to make sure that those are actually the parameters that are going to be passed in, and they're not going to be modified to some random other value that you can't reason about when you just see the declaration of that function, right? That does not make sense. Like those post conditions, anything in there could have any value. You wouldn't be able to say anything about that. They would be useless. So parameters have to be const if you want to refer to them in a post condition. What else do we have here? Not part of the immediate context. Wait, is this the... Hey, hang on, can I just break for a second? Okay, so I have those slides in there, interesting. Those are some corner cases which I don't really want to spend much time on. You got to make the template specializations independent from the primary template. You have to make them not part of the immediate context, so you can't sphere on them. Again, don't want to spend too much time on this. This is a more interesting one. You should not be able to capture a variable in a contract assertion if it's on a lambda. So we added this rule that if you refer to this I here from a P or post a contract assert, and if that would trigger a implicit capture because this lambda has a default capture there, you make that all form. Because otherwise, the mere act of adding the contract assertion, even if it's never checked, would make a copy, change the properties of the lambda type, right? It would potentially slow down your code because you would have to copy the thing so that it's captured in a lambda. It might make your lambda no longer trivially copyable, all of that stuff, even if you're not checking the assertion at all, right? It would modify your program, potentially lead to extra things happening. We don't want that. So we make that all formed for pre, for post, also for contract assert, right? But if you have another statement there that captures the I here, then it's fine, because then the contract assert is not the thing that's triggering the capture. It's already triggered from somewhere else, so that's fine. Also, if it's explicitly captured, that's fine, because again, like it's still going to be captured if you don't have this contract assert there. Referring to static variables, it's fine because they're not going to be captured, right? You can just refer to them. You don't have to capture them. Right. So what happens then when you actually evaluate one of those contract assertions? So we have these three kinds: pre, post, contract assert. So they are evaluated at different times. This is effectively the main difference between them. So we evaluate precondition assertions when we call the function, after initialization of the function parameters, and before we start evaluating the body. We evaluate post conditions. That was the thing I was kind of referring to earlier. After the result object value have been initialized, and after local variables have been destroyed, but before destruction of the function parameters. And then assertion statements are just executed whenever you reach that statement, right? So that's when we're going to evaluate these things. What happens when we evaluate them, right? So for example, here we start calling this function, right? Some of these calls violate some of those contract assertions. What happens, right? So we need some kind of switch, right? To like either turn checks on or off. That's kind of the simplest thing. But we actually have more than just one switch. In fact, we have 4 possible evaluation semantics. And every contract assertion can be evaluated with one of those 4. So those are the 4 options that we're giving you. You can either ignore, which means don't do anything. You can observe, which means check the Boolean expression. If it fails, call a contract violation handler, then keep going. Then we have enforce, which is if there's a contract violation, call the contract violation handler and then terminate. And then the 4th one, we just added in Tokyo. So this is like fresh from the press, brand new. Quick enforce, which is check the predicate, and if that fails, just immediately terminate. Don't call the violation handler, don't call anything. Just immediately terminate the program, which is kind of what you want to do in a safety critical context, right? You want to minimize the attack surface. You don't want to start calling into other functions if you know there's something really wrong here. You just want to terminate as quickly as possible. And the other reason to have this is you want to minimize code bloat. So instead of calling, terminate, which is a function call, and call a violation handler, which is another function call, you want to be able to just say, okay, we're going to just insert one trap instruction there, like Clang, for example, built-in trap, 1 instruction, 1 byte, you're dead, right? So to just have like minimal code. So this is what you would do, for example, in a hardened release build, where you want to have a release build that's like really fast and small, but you still want your contract assertions to be enforced because, for example, out-of-bounds access is just unacceptably bad in a safety-critical context, right? So that's the semantic you want to use there. I should say terminate the program doesn't mean call abort or call terminate. We have been going on like back and forth on this a lot. And then we agreed we don't specify how the program is terminated, right? So in some cases, you want to call abort because that's the thing that cassert does if you want to be compatible with that. In other cases, you want to maybe just call the trap instruction. So if you don't specify what you get, the compiler can choose whatever is most appropriate for that particular semantic. So we just say terminate the program in some implementation-defined way, and the compiler can basically choose whatever is most appropriate for their users. So we don't specify that. Ignore, we call an unchecked semantic because it's not checking the predicate. The other 3 are called checked semantics because they do check the predicate. And the last 2, enforce and quick enforce, we are calling enforcing semantics because they are enforcing the contract assertion in the sense that if you have a violation, you're not going to keep going. And so we have these 4 implementations also allowed to add more non-standard ones as an extension. And then we say that the mechanism which one you get is implementation defined. So we're not standardizing anything like ndebug or build modes, which is something that's the CSS 20 version standardized build modes. We figured out that's basically not good because you're gonna force everybody to like ship multiple binaries of everything. Like we don't want that necessarily. So we say the mechanism how you choose which contract semantic applies is implementation defined, right? We don't say anything about this in the standard. The compilers can figure out whatever flags or settings or build modes they find most appropriate. They can do this at compile time, at link time, at runtime. For example, if you have a C++ interpreter, you might want to change at runtime what the semantic is. That should all be conformant. You do have 3 pieces of recommended practice, though. It's like the compiler doesn't have to do this to be conformant, but it's strongly recommended that you have a mode where all contract assertions are ignored. There's a mode where they're all enforced, and that enforced is the default, right? So that's basically what cassert does as well. So that maps to like debug and release, where in debug everything's enforced, and in release everything's ignored, and debug is the default if you don't specify any compiler flags, right? So that very like intuitively maps to like the typical compiler flags that we have today, where you don't prescribe that a compiler has to do it exactly this way. You can do something else. So when you check the contract predicate, multiple things can happen. The predicate can evaluate to true, and then we know there's no contract violation, we're good. It can evaluate to false, and then we know there's a contract violation. And then there's 2 more things that can happen. One thing that can happen is that we failed to evaluate the predicate because, for example, while we were evaluating this Boolean expression, there was an exception, so we didn't finish. So we call this a contract violation as well. I put this in quotes because you didn't actually manage to check whether it's a contract violation. So technically, it's not necessarily a contract violation. And people have commented on this that, I'm not sure if this is the right terminology, but we decided to call it a contract violation anyway, because you wanted to end up in the same handler, in the same callback. It doesn't make sense to have like a second different callback for the situation. And it's called the contract violation handler. So it's kind of, you want to treat it as if it was a contract violation, because it's something that went wrong while we're checking it. We're not sure if the contract is not violated, right? So it might be violated. So we can't tell. So we treat this as a contract violation. And the fourth case is we don't finish evaluation of the predicate, but we also don't know because control flow just left and never comes back, like long jump or terminate, or maybe the thread is infinitely suspended and we never return back to the kind of the contract check. So in that case, you just get what you get. If you long jump while you're evaluating a predicate, you just long jump. Okay. So now when we have detected contract violation and we are in observe or enforce, so not quick enforce just terminates immediately, but observe and enforce call the contract violation handler. So what is that? What will happen then is that the compiler will create an object of type contract violation. That's an object that has a bit more info about what happened. It's going to call the contract violation handler, and it's going to pass this contract violation in by const reference. And the other thing is that if we got an exception while we were evaluating the predicate, you also get to access that exception via the current exception. And so the contract violation handler itself is a function that's named handle contract violation with that exact name in the global namespace. It takes that argument, it returns void. It might be no except false or no except true. You don't specify that. That's interesting. There's no declaration of it provided in the standard library, but there's default implementation, which recommended practice is it just prints some info to std out, which is kind of what assert does as well. And then we allow it to be replaceable, which is the same mechanism we already use for operator new and delete. If you want to define your own, you just supply your own definition of that function at link time and you link that in. Okay, so at link time you can replace, I think the kind of compiler term for this is weak symbols. Maybe somebody's familiar with that. That's exactly what this is. You provide your own definition, it's going to replace the default definition. And your own definition can do whatever it wants, right? It just has to have the right name, the right signature, and then you get this contract violation object. You can log it yourself if you want to do your own logging. You can phone home and like send it to the server or something. You can also then call the default one afterwards if you want to fall back to that. There's a special function for that, invoke default contract violation handler. You can do other stuff. You can set a breakpoint. That's another feature that we're going to get in CSS 26, yay. And you can throw an exception. So that's interesting. That's what kind of John was talking about in his talk earlier. That might be very useful if you want to handle, portably handle a contract violation without terminating and also without continuing into buggy code. You kind of have to follow the Lakos rule if you want to do that. So you can't sprinkle no except all over the place. John talked about that quite extensively in his talk, so I'm not going to repeat all of that, except that the way we specified this is that if you do have no except here and you throw from this pre, this is considered to be within the no except boundary, right? So if you do that, you get terminate. So you still have to follow the Lakos rule even with a new shiny contexts feature, which is why sprinkling no except all over your code is a bad idea. John just gave a talk on this topic. I also covered this in my other talk last year. That was a CPP and North keynote where it touched on this as well. There's a bunch of papers that a bunch of people wrote why this is a bad idea, et cetera, et cetera. Contact assertion doing constant evaluation. I'm kind of running out of time, so I'm going to skip through this very, very quickly. Basically, what you want is you don't want to repeat, like if you have a function that can be either called at compile time or at runtime, you want the contact assertions to be checked in both cases. You don't want to have to repeat them as static asserts if you want them to be checked at compile time, right? So you want to have a contact violation either at runtime or at compile time, depending on whether that function is going to be called in a constant evaluated context or not. So that just works. So if it evaluates to true, it's fine. If it evaluates to false, you get a contact violation. If it's not a constant expression, that's an interesting case. We can't then make the whole thing not a constant expression because you can sphere on that. That will violate our principle. that you shouldn't be able to sphere or reflect on whether the contract assertion is there. So what we say is, well, if the predicate is not a constant expression, the actual assertion still is one, but it's a contract violation. So what happens if you get a contract violation at compile time? Obviously, you can't get a violation handler call at compile time. So what you get instead is, again, the compiler is free to choose what semantic is going to be applied. Ignore does nothing, and observe and enforce perform constant evaluation, and then if it fails, observe gives you a warning, and enforce makes the program formed. And the fourth one, quick enforce, is not on the slide yet, but it's going to do the same thing as enforce. It's going to make your program formed. This weird thing called trial constant evaluation, for which we need a special rule because you have functions that might or might not be no except, and then if you use them to initialize a const int, that might be initialized at compile time or at runtime, and by adding a contract assertion, you don't want to flip which one it is. That would be bad. That would, again, violate the principle, so we need a bunch of extra rules to make sure that never happens. Recursive contract violations, there's two options. Either we could prevent recursion, because that seems like bad, right? If you would get like a contract violation while you're handling a contract violation. So previous proposals said, okay, you're going to prevent this by saying that while you're handling a contract violation, you're going to disable contract checking. Turns out that's actually really bad, because then all the code you're running while you're handling your contract violation is potentially unsafe because all checks are off. That's really bad. So we decided that the safer thing to do is to do nothing. You get what you get. If you hit another contract violation while you're handling a contract violation, you get a recursive call of the violation handler, and it's up to you to handle that. And if you don't, you get a stack overflow and you crash, and that's hopefully going to be something that's really obvious and easy to fix, rather than just disabling checking, which is not obvious and a lot more unsafe. We have a little bit of library API here in this proposal. I'm going to go through this very quickly. You only ever need this if you want to implement your own violation handler, not just to use contract. So there's a very limited set of people that will ever have to do that. At most, one person per company, I think. Everything is in header contracts. Everything is within that in namespace contracts. That was a little bit controversial that we want to have a nested namespace, but we decided we really, really do. Let's see what Luke says about that next meeting. We have this one class, contract violation. It has this API. Source location, that's a memo function that tells you where the contract violation happened. Comment, which tells you what the expression was that was violated as text, human readable text. Both of those don't have to give you that. Like if you, for whatever reason, you don't want to store your code in plain text, or you don't want to store source locations in your binary for safety reasons or binary size reasons or whatever, you can just return an empty string and a default constructed source location. That's also conformant. It's just a recommendation that that information is returned. Detection mode returns a little enum that tells you what happened. Did it evaluate to false, or did I get an exception? We have semantic, which returns another little enum that tells you, is the contract enforced or observed? Note that ignore and enforce fast are not in this enum because those semantics never call the contract violation handler. And then the last one is kind, which tells you, was it a pre, post, or a contract assert? We can't use contract assert there because it's a keyword, so we just use assert. Hopefully that's not going to be confusing. And then we have this little free function here that lets you call the default violation handler from your own violation handler. Right, we say that the standard library itself does not have to add any of the stuff. Like we don't add contract assertions to the specification of the standard library, but we allow implementations to use them internally. So that's fine if an implementation of the standard library chooses to use these things in their own implementation. That's cool, but we don't demand that. We don't say that every precondition in the standard now has to be a preconditioned assertion on that standard library function, and there are good reasons why you don't want to do that. All right, so that's the proposal. In the last 10 minutes that I have, I want to quickly go through the open design questions that we still have, that we thought we didn't, because in issue 21 we agreed, this looks great, this is what we want to ship, but then it went to the next level, the design revision groups, evolution, library evolution. They said, I'm not sure this is a good idea, so we have to rediscuss this. So let's go through those. So we have basically 5 of those. There's more things that individual people kind of disagreed with or had concerns about, but those are the 5 things that evolution as a whole, the evolution working group as a whole, voted, and there was a significant number of people that said this is a concern for us. So those are those 5 things. The first one is, what do we do about UB? There's 2 cases here. One is, well, it's kind of maybe surprising because contract assertions are there to prevent UB, mitigate UB, but turns out if you can still get UB, and there's some interesting situations there. One is, okay, here's a function that has UB, right? We are dereferencing a pointer and we're passing it a null pointer, right? So that's hopefully you can all agree that's UB. Now we add a precondition assertion that pointer is not null. So hopefully that's no longer UB, right? We're gonna find the bug. Well, obviously if you ignore the precondition, then it's still UB because you're ignoring it, you're not checking it, right? If you're enforcing it or quick enforcing it, you're gonna terminate, right? At the point where we hit that. So we're never gonna go into the body of that function. So again, we don't have UB. This is well-defined behavior, this is fine. But if we have the observe semantic, then we keep going into the function body, right? And so it turns out that if we keep going into the function body, the compiler can say, oh, but that's UB, I can't get there. So, and then it can optimize all code paths leading to that std out line, including the precondition assertion. Can just optimize that whole thing out. And people are saying, that's maybe not good. We should maybe do something about this. But the program has UB, so what do we do? And the other case is if you have UB inside the predicate itself. For example, here, we have a function that adds 100 to another integer, right? So that might overflow, right? But it's undefined behavior if it overflows, so the compiler can assume that it never overflows, right? And optimize based on that assumption. That's what a UB is, right? And so then if you have a precondition assertion that tests that S of A really is bigger than A, the compiler can say, well, this can never overflow. Therefore, the result will always be bigger than A because we're adding 100 to it and that will never overflow. Therefore, this is just pre-true, right? It will always be true. And it can just elide this entire precondition check there. Just elide it out, even if it's enforced, right? And so again, people say, that's not good. The problem is, what do we do about it? So the first case is where we have undefined behavior after. Like, we don't have anything in the language to mitigate that because UB is UB. The standard does not place any restriction on a program that has UB. But maybe we can do something. There is this paper by Davis Herring to introduce the concept of an optimization barrier so that time travel optimization cannot elide that. So we can specify that a contract assertion is such an optimization barrier. That paper is not in the standard yet. It's not past evolution. So maybe we can do it, maybe not. Let's see. And the case B is undefined behavior while evaluating the contract assertion. Well, we just really don't know how to do this because this reduces to the problem of how to have a language that has no UB, essentially, right? So there's a paper at P2680R1 which says, well, maybe we should constrain contract predicates to a subset of the language that we know doesn't have UB. We discussed this at length. SC21 doesn't feel this is the right approach. Like, if you want to specify a safe subset of C++, you should probably do this for the whole language and not just for predicates inside contract checks. That's kind of weird. So we decided not to do that, but then it came back, and now SC23, which is the Safety and Security Study Group, is considering this idea, and we're basically going to do whatever they tell us. So this topic is going to come back. The second one is, should the compiler be allowed to elide a duplicate assertion evaluation? So that's a tricky one. So this comes back to the question, what happens if a contract predicate check has side effects, which is something you don't really want to do. You want to check something, observe something. You don't want to modify anything, right? So you don't really want to have side effects. But sometimes they're useful. They're good use cases for this. Like, maybe you want to check something and the algorithm for that requires an allocation. Or you want to check a Boolean flag, which is behind a mutex because many threads are like checking it. And then you want to be able to lock and unlock that mutex to do that check, right? So you have to allow side effects. CSS20 contracts just said it's all UB, and I think that's a spectacularly bad approach, so we're not going to do that. So we're just going to allow them. But then the current paper says that if the compiler can tell whether the predicate evaluates the true or false, somehow prove it statically, it doesn't actually have to evaluate it, which if it's a side effect-free expression, you're not going to observe the difference, right? But if it has side effects, those side effects might just not occur. A little bit like copy elision, where you have a copy constructor that prints something, but then you actually end up not printing anything because that copy was elided. So it's a little bit like this. And the paper also says that these side effects could occur multiple times. And there are a bunch of reasons for that. Two of them are we want to discourage predicates that have side effects further by saying, well, you can't rely on those side effects happening at all, or one time or twice or any number of times. You just don't know, so don't rely on them. And the other interesting reason to do this is that you want, for example, if you have a program, you have an application and a dynamic library, you want to enable callee site checking in the application and caller site checking. Sorry, the other way around. You want to be able to either enable contract checks in a library or disable them, and also enable caller side contract checks in a program that's calling that library, or disable them. And you want to have both versions, the applications which checks on or off and the library which checks on or off, be able to like talk to each other, like load the dynamic library without having to care about which one it is, without that being an ABI break or having to recompile. And in that situation, if both the application and the library have checks enabled, you might end up checking something twice. And like in order to not have that, you would have to then recompile the program with caller side checks off, or introduce some kind of mechanism to detect that, which would be an ABI break and potentially more symbols in your library and stuff like that. We don't want that, so you might want to, enable checking something twice. So effectively, if you have a side effect in your precondition check that increments something, like don't do that, this is just to show off like what the specification is, but don't actually do that, you can't rely on what I is. It might be 0, it might be 1, it might be 42. You don't know. But then, like, the observation was, well, but there are assertions. This is like an example adapted from the Clang source code, and those things are actually quite common. For example, an assertion that something isn't called recursively more than n times, and there the assertion maintains a counter. And if you can't rely on that counter being evaluated, like incremented exactly once whenever this thing is checked, then you just can't write that. I mean, there's other reasons why you can't write that with contracts. We don't have anything like ndebug that lets you selectively not declare that variable when contract checks are off. We don't have that kind of mechanism, but that's another topic. Like, even if we have that, like, you can't rely on the ++ depth occurring once when you check that, which means those counter assertions, they don't work. And there are people who say that's bad. That means we can't migrate from macros to contract assertions because we can't write those if we don't know how many times it's going to be evaluated. So some people are saying, no, it must be like this. Other people are saying, no, this is really bad. The room is kind of split halfway on this topic, at least in evolution. I think in SG21 we have more of a kind of, we want what's in the paper right now, but like evolution is split halfway. We need their consent to put anything in the standard. So you're going to spend more time discussing this. The third open question is, should the contract violation be allowed to throw? There's a massive upside to this, which is we really need that. So we have some mechanism that if you have a contract assertion violation, we don't want to continue into the buggy code. That would be really bad. But we also don't want to terminate the app because there are use cases where you can't terminate the app. Like, as John was saying in his talk, in the financial industry, for example, you got to keep the exchange running. You can't just terminate. So the only other portable thing we can do is to throw an exception, unwind the stack. But the con of that as well, then it means any assertion can throw from anywhere. Some people have a problem with that. And also, if you sprinkle no except all over your code, that's just not going to work because then you're going to terminate, which is the exact thing that you wanted to prevent by using a throwing violation handler. So again, the room is split on whether we should allow those. We're going to discuss this more at the next meeting. There's a question whether we should allow observing and ignoring contract violations at compile time. The argument against it is, well, if you know at compile time there's a violation, we should always error out. The argument for it is, but then we need to check all predicates at compile time. That might be very expensive in terms of compile time. You want to be able to switch that off without having to put it behind macros. And the last one is virtual function support, which we just didn't get done yet. It's complicated. I don't have time to go into this. I have 20 seconds left. So yeah, there's all of these approaches that have been used in the past. They don't quite work. We have a possible solution. There's this paper. We haven't had time to discuss it yet, so we decided, let's keep it out of the MVP. Let's add it later. But then evolution said, well, maybe if you don't even support virtual functions, maybe it's not really viable as a proposal. You should really add that and then come back. So we're going to do that. We have a bunch of things that we already know we're not going to add. In this revision, this is this list. Virtual functions are an exception. They might get into the MVP. Everything else here, there's a lot of interesting features here, which we know we are not going to add to the MVP, but we'll get later, possibly in C++29, or maybe even within still the C++26 timeframe, but not in this paper. Okay, and that's all I have. Thank you very much.